Okay, so this is our companion VR to the other VR movie that talks all about our model selection and more details. But all the details are in this paper that was published in Applied Spectroscopy. And if you can't find that paper, you can email me and I'll send you a copy of that paper. And so what we wanted to be able to do was visualize our regression vectors in VR and indeed check that they are diverse models, that they have different shape. And we did that like shown in the other movie with our machines. We did that via a cosine theta, the angle between them. But we have these, where do we get these regression vectors? Well, we have our training samples. I'm an analytical chemist, so the labels typically here are analyte concentrations. And over here, typically we work with spectra. So for each sample, we have a corresponding measured spectrum. And there's this nice simple linear relationship we use. And so we just want this model, the regression vector. Typically we use PLS, partial least squares, to get that regression vector. And once you do have it, you can interproduct that with your training samples, but more importantly, our target samples, and get the estimated analyte amounts. And hopefully this y hat is close to truth. And so we had this autonomous approach, model diversity, prediction similarity. So we wanted the models, they should have good diversity, like I said, by a small cosine theta value. And yet we want them to predict these target samples, these y hats on the target sample, they need to be same. That's the idea. So we just wanted to be able to do in the VR is to touch one of those model pair glyphs and have it pop out a regression vector, but make it in 3D, give it a glyph in the VR. And we formed those glyphs by just taking, this is an example regression vector across our spectral wavelengths. And we just spun it essentially around the zero line, and that's the axis down the glyphs here that we created. And so if a regression coefficient is like going from, let's say from here to here, it's staying in the negative area, so these are black. And if the regression coefficient, like from here to here, it stays in the positive area, then these are the red regression coefficients. And if you cross the zero line, like we say here, we go from positive to negative to positive or positive to negative, then we are color coded to the white. And so this is an example of the regression vector like this. Neither one of these is this particular regression vector, but that's the idea. And so we just want to be able to touch a glyph and indeed see how diverse these are, or how non-diverse or similar they are. And also in this was our early work in the VR of this model selection. We created this scoreboard so we can select models and see how our prediction errors are, as well as we can select a pair of models, just one glyph, and see how those two individual models, how their prediction similarity is. So this is the movie. These are tense structured glyphs. They have no relationship. There's no model features, unlike the other one with the ball and spikes. There's no model features attributed to these. We just wanted some general glyphs because we were just initially first work was trying to just create regression vector glyphs. So here you can touch a glyph and you can pop out your two regression vectors and see, like I said, indeed these are very diverse. They don't look anything like each other. And then one can then go to the scoreboard and see how well they predict, if they predict similarly or not. And then, so one could go to each glyph and individually select those glyphs if you wanted to in the VR by just visualization relative to their spatial coordinates in the VR landscape. All right, so again, this work is all very well spelled out in the applied spectroscopy paper. And with that, I thank you for your attention.